block diagrams are used to represent what? Different transfer functions in a system, right? So in simple systems, we have one or two block diagrams. So for example, if you take a look at this system, it's two blocks. But in very large complex systems, we have what? Many blocks to represent the transfer functions of different subsystems within that system, right? So that makes it difficult for us to analyze the performance of the system because what? So many transfer functions, right? So in order to simplify that, we use what? Block diagram reduction. Our aim is to reduce the block diagrams as much as possible, right? The optimal way to do it is to reduce all the blocks into one single block, which represents the whole transfer function of the system, right? So
Sir, my electricity is gone, so if my laptop's charge is gone, so I may got disconnected. So,
okay, try to use your mobile in that case if you can.
sir, I'm using my mobile data now, but I don't know how much time I'll be able to use it.
Okay, so as long as possible, you can. There's nothing to be done, right, about that. So anyway, let's start with the simplest ones. So there are some simple configurations of block diagrams which we can reduce to a single block, right? So the first one, blocks in series, right? So this is pretty easy to see. So we have the input X, we have two blocks G1 and G2 which are in series, and we have the output Y. So in this case, it's very easy. The overall block diagram of these two blocks would be G1 multiplied by G2. So it's very easy to see. So from the first block, the signal that you get is X multiplied by G1, this one, right? Then X multiplied by G1 enters this block where it gets multiplied by G2. So basically Y is what? X multiplied by G1 multiplied by G2. So in that case, the overall transfer function of the system becomes G1 multiplied by G2, right? So let's see how it's done in MATLAB. Same as usual. So you have numerator and denominator, and then use TF to describe these transfer functions. So we have G1 and G2. Now to find the overall transfer function, we use a very simple command called series, right? So for series, just write overall transfer function G3 series G1 comma G2, and we have our overall transfer function where G1 and G2 are in series. So as you can see, using the series command, it basically multiplies G1 and G2. So same thing. So if we multiply G1 and G2, what will happen directly? So G3 equal to G1 multiplied by G2. Same result, right? Because series means two blocks in series means they will be multiplied. The transfer functions will be multiplied. So that's series. The next one. So these blocks are in parallel, right? So again, whenever you have a massive block diagram, you see that these series configurations, parallel configurations are very easy to spot. So you have to spot them and then reduce them. So this is a parallel combination, and it's always like this. There's no other type of parallel combination. For example, in this summation block, summation junction, if one of the signs is minus instead of plus, it's no longer a parallel combination. Okay, so it's very easy. So our input is entering two different blocks, G1 and G2. It's getting added up, and then we get the output. So the first signal is X into G1. The second signal is X into G2, and they'll get added, right? So XG1 plus XG2. So our overall transfer function is G1 plus G2. So this is the overall transfer function of two blocks in a parallel, right? So for this one, very easy. So use this command, parallel, directly. Right? Also, we can do the same thing if we just add them, G1 plus G2. Same result, right? addition and using the parallel command are the same thing in this case. The last simple configuration is the feedback configuration. You already know about this, positive feedback or negative feedback. So feedback basically means what? We have the input, it's going through a forward path represented by G1 in this case. Then we get the output, but the output is again fed back to the input. So the output goes through a feedback path with a transfer function of G2, then is added or subtracted from the input. So if it's added with the input, we call it positive feedback. If it's subtracted from the input, we call it negative feedback. And for each of these configurations, there's a formula. For positive feedback, we have G1 divided by 1 minus G1 G2. So this is the overall block diagram, meaning overall transfer function of this block diagram. G1 divided by 1 minus G1 G2. This one. If it's G and H, we have G divided by 1 minus GH. If you reduce it to one single block. For negative feedback, just replace the sign minus. Instead of minus, it will be plus. So G divided by 1 plus GH. Very simple. And again, similar to series and parallel, we can just directly use the feedback command, right? So we have already defined G1 and G2. So the overall transfer function G3 would be feedback G1 comma G2. Now, how will you specify whether this is positive or negative feedback? So out of these two, one of them is the more generally used type of feedback. Can anyone tell me which one?
So negative feedback.
Negative.
Yeah, negative feedback. Positive feedback is usually not used that much. Do you know why?
So it increases the noise in the system.
Well,
Instability.
not actually the noise. So
So
feedback,
it makes the system unstable. I mean,
Yeah.
it's oscillating.
yes, so that's correct. So it makes the system unstable. How? So by using positive feedback, you're continuously adding the output with the input, right? So as a result, the overall output, new output will get what? Will continue to increase until it becomes out of control, right? It increases to infinity, so the system will become unstable. It doesn't happen always, but it's very likely to happen. So in that, that's why we normally don't use positive feedback. We use negative feedback for various purposes, for error correction or to get the desired output or to make the output within a certain range, etc. Right? That's why we use feedback. But with positive feedback, the system might become unstable. So default is negative feedback, and the MATLAB feedback command assumes the same. So feedback G1 comma G2, it will assume negative feedback, and this is the transfer function. If you want to signify, if you want to represent positive feedback, just give a +1 at the end. Now this will be positive feedback. And this is the transfer function that you'll get. Okay. Same.
Yes, sir.
Yeah, the code is written in the same manner here, only now you'll get the numerator and the denominator of the overall transfer function, and then you can use TF, same thing. So any questions up to this part? Series, parallel, and feedback?
No, sir.
No, sir.
Okay, it's pretty easy. Next, observing step and impulse. So the next part, we'll observe the response of the system to different types of inputs. So in the first lab, we already observed the step response, right, by using the step command, but we haven't seen the impulse one. For the impulse response, it's the same thing, impulse transfer function. There's a direct function called impulse, so you can use that to observe the impulse response. So how to reduce this block diagram? It's pretty simple, right? Can anyone tell me what are the steps?
G1, G2 divided by 1 minus H G1, G2.
Okay, let me do one thing. Wait. Okay. What did you say? Please repeat.
Sir, G1, G2.
G1 and G2 will be in series, first of all, right?
Yes, sir. So
Then?
It will be feedback, negative feedback with H.
Yeah.
Yes.
So you can use series G1, G2 first, then use feedback command, or since we know that series means multiplication directly, you can directly use the feedback command. So G1 multiplied by G2, it will be in feedback with H directly, right? And
Yes,
then you
sir.
can use step for the step response and impulse for the impulse response. So let's copy this part. So this is the system, overall system. And we have the step and impulse responses. So the step response, you already know why it's like this, right? It eventually becomes equal to the input and it looks like a step response. So you already know this from the first lab. What about the impulse response?
Sir, it is initially 1 and it drops to 0.
The impulse input is initially 1, means sorry, not 1. At time t equals to 0, it's a very large signal, right? The impulse input.
Yes, sir.
And after time t equal to 0, it becomes 0 directly.
Yes, sir.
And the output, as we know, will try to follow the input, right? So it will start off at its maximum value, but as time goes on, it will eventually become equal to 0, which is the final value of the input, right? So in this manner, the output becomes equal to the input, but it takes some time to do so, isn't it?
Yes, sir. Yes.
So this is how you can tell that this is the impulse response. It eventually becomes 0 after a certain amount of time. Okay, so again, what is the purpose of observing these responses? Step, impulse, just so that we can understand the behavior of the system. And these inputs, these input types, they are the simplest types of inputs, right? We call them test functions. So using these test functions, we can observe the behavior of a system, right? The third type of test function is called a ramp function, and the response that we observe for a ramp input is called the ramp response, right? So what is a ramp function?
Sir, it is 0 before 0 and after 0 it has a slope of 1.
So basically this is a ramp signal, right?
Yes,
Isn't
sir.
it?
Yes, sir.
It has basically a positive slope. That's it.
Yes, sir.
So how to observe the ramp response in MATLAB? The thing is, there is no direct command like step and impulse. You cannot use ramp. There is no ramp command. So for that, you need to do some manipulations to your transfer function. So let's see how it's done. Normally, I would explain this using a board. Okay. So let's start with the transfer function. So suppose the transfer function is g. Let's use the symbols in the lab sheet for less confusion. So we have y by r, y and r. So g equal to y. So suppose we have r, which is the input. We have g, which is the TF. We have y, which is the output. So what is the normal formula? So g equal to y divided by r, right? Transfer function equal to output divided by input.
Yes, sir.
So suppose we are given a particular transfer function g and we are told to observe the ramp response, right? So first of all, we have to do some manipulation. So ramp response. So what is the Laplace domain representation of ramp?
Sir, 1 by s.
That's the representation for step.
So 1 by s square.
1 by s square. That is the representation for ramp. So let me write this. Ramp is 1 divided by s square, right? So in that case, suppose we make the output the subject. So y is the subject now, the output. Y equal to g multiplied by r. So for observing the ramp response, we will multiply the transfer function with 1 by s square. So 1 divided by s square. All right. So this is for observing the ramp response. So how you can write this as G multiplied by 1 by S multiplied by with another 1 by S. Can you do that?
Yes, sir.
Yes,
Same
sir.
thing. So again, as what is 1 by S?
The unit is step response.
Step response.
The Laplace
It
transform
is
of
the, yeah.
step response.
Yeah, it is the Laplace domain representation of a step function. So suppose we take this one of the 1 by SS back towards the left hand side. So y divided by 1 by S equal to G multiplied by 1 by S. Right? Is it clear?
Yes, sir.
So y is the output 1 by S. So now the left hand side is a form of output divided by input, isn't it?
Yes, sir.
But in this case, the input is a
Step response.
step function. So in this case, the input is a step function. So can you not say that this transfer function, it will give us the step response, right?
Yes, sir.
Basically what I mean, if we now use step G multiplied by 1 by S, will it not give us the step response? Because on the left hand side, we have output divided by input, which is the transfer function formula. And in this case, the input is 1 by S, which is basically a step function, right?
Yes, sir.
But remember, we started off with the input being 1 by S square, didn't we? So that means by observing the step response of G multiplied by 1 by S, you're actually observing the ramp response of G.
Yes, sir.
So is this part clear to everyone?
Yes, sir.
Again, in order to observe the ramp response of G, we just multiply G with 1 by S and observe the step response. That will give us the ramp response. And there is no direct ramp function, so we have to use step. Any questions? No, okay. So what is a transfer function GS? It's 1 by S squared plus S plus 1, right? If you multiply 1 by S squared plus S plus 1 with 1 by S, again, we'll multiply the transfer function with 1 by S. So in that case, we'll get 1 divided by S cube plus S squared plus S, this one. So numerator will be 1, denominator will be 1, 1, 1, and then there is no last constant term, so 0. Then we use step, num, comma, den. And this will give us the ramp response. So Control C. So this is the, it says it's the step response, but this is actually the what?
Ramp response.
Yeah, it is the ramp response. And because we multiplied the original transfer function that we were supposed to get the ramp response of with 1 by S. That is how we get the ramp response using the step function. So by looking at this ramp response, so can you tell me how it looks like a ramp response?
So
Because from 0, it started a slope.
Yeah, it looks like a ramp function itself,
Yes, sir.
right? It's also positive slope.
Yes, sir.
So it's also what? Trying to become equal to the input. And that's how it's easy to identify that this is a ramp response.
Functions.
Yeah, ramp response. Okay, so this part, up to this part, any questions?
no, sir.
Okay, so we have observed the output of the system for 3 different types of inputs: step, ramp, and impulse. So those are the basic test functions, as I mentioned earlier. So it's very useful to observe the responses of the system when the inputs are those 3 functions. What if we wanted to observe the response when the input is any function? right? Any time dependent function, like suppose sine function or an exponential function or a logarithmic function. So for that, we use a function called LSIM, which is basically linear simulation, right? For that, we have to, there are 4 input parameters. So num and den, you already know what they are. They are the num and the den of the transfer function that we have. R is the input signal, right? And T is the time interval for which you want to observe the response, right? So suppose our transfer function that we have is 2 by s plus 3. We want to observe the response of the system when the input is given by e to the power minus t, which is an exponential function, right? E to the power minus t. So very easy. So first write the num and the den. Okay, so clear all CLC. So we have written the num and the den. Next, define the time interval for which we want to observe the response. Suppose from 0 to 6 seconds. And then write the actual input function itself, which is e to the power minus t. R equal to e to the power. Oh, it's become a little messy. So again, let's try num den t r. So we have our 4 input parameters. Now we just use LSIM num, den, r, t. So this will give us the response of the system for an exponentially decaying input function e to the power minus t, and it will show us the output for 6 seconds, from 0 to 6 seconds. So these are the results. So in this plot, one is the input function, the other is the output. Can you tell me which one is which?
Sir, blue one is the output, sir.
Yeah, blue one is the output, and the upper grayish black one is the input, right? Because input is e to the power minus t, and this is obviously e to the power minus t. And this is the output. Again, as you can see from this response, it's following the usual trend that we know, that the output will try to follow the input. So the output, the input starts off at a maximum value at time t equal to 0. The output starts off at a maximum value close to that time. Eventually, the input will become 0 at time t equal to infinity. The output, as you can see, will also become equal to 0 after a certain amount of time, right?
Yes, sir.
Clear? Okay. So suppose we want to observe for a longer time, 60 seconds. Then use LSIM. What is the issue? When simulating the response to a specific input signal. All right, I have to do R also. Okay. Yeah, so as you can see, as time approaches a large value, the input is obviously becoming 0. The output will try to follow the input, and it will also what? Eventually become equal to 0.
Overlap, sir. Yes.
Yeah, this portion, right? So that is observing the response for any arbitrary input function. What if the input function is a sine function? So suppose let's make t 6 seconds again. Suppose r is, instead of e to the power minus t, it's just sine t. Then again use LSIM. So this is giving us the what? Response of the system to a sinusoidal input function. And as you can see, the output is also a sinusoidal function, but it's slightly delayed because it will take some time. It will try to follow the input, but it will what? Have some time delay as usual, right? So the upper one is the input and the blue one is the output.
Yes, sir.
So this is a very useful function, LSIM. Using this, you can observe the response to any type of input, any type of time varying input. Simplification.
Dynamic system.
Yeah. Simplification using Simulink. We don't need to do this for this lab. Assignments. So for the assignments, there are some block diagrams, big ones, which you have to reduce using MATLAB, block diagram reduction. 1 and 2 are pretty easy. Starting from 3, the thing is it's not only a little more complex, but also we have multiple signals. Not in addition to the input, we have multiple signals. So for that, you need to use a different approach, which we'll learn later on. 1 and 2 are pretty easy. You can use your basic, so far what we have learned, you can use that. So looking at these 2 block diagrams, can you identify the different configurations and then reduce them step by step? Suppose
Yes,
number 2, how to do that for number 2?
Yes, sir.
I mean, can you identify the individual configurations and reduce them?
Yes, sir.
So can anyone tell me how? Number 2.
Sir, the top part, the middle one is in parallel and it is in series.
No. Which one is in parallel?
It is feedback, negative feedback.
Yeah, G1 and G2 are in a feedback configuration, right? So use the feedback formula, which was for negative feedback. I think it was what? G1 divided by 1 plus G1, G2, right?
Yes, sir.
So you make one block like that. Then whatever block you'll get, it will be in series with what?
So KC and G3.
KC and G3. So these 3 blocks will be in series. Then you make them series. And then this overall block will be what?
Negative feedback.
Yeah, again, negative feedback with the block H. Then you'll get a single block. That's it. Number 1, it's also pretty easy. G1 and G2 are in parallel. Then series with GV and GC. Then negative feedback with H. From 3 onwards, you have to use a different method, which we'll learn right now. Topological reduction of block diagram. So again, if you take a look at 3, let's take a look at a more complex one. Suppose 6. So can you identify the individual simple configurations in number 6, like series, parallel, or feedback?
Yes, sir.
Okay, which one? Which one is series or parallel or feedback in this one?
Sir, H2 is feedback.
With what?
G3 and G2 and
So
L.
what about the summation thing in the middle with an extra signal L2? Can you tell that they're in feedback if it's like that?
No, sir.
It's not easy to understand this one. What about this one? Again, same thing. You have an extra summation junction and also an extra signal. Okay, so these are not easy to identify. So you cannot use MATLAB functions like series, parallel, and feedback directly to reduce these block diagrams. So for these large complex block diagrams, we use topological reduction. So again, take a look at this particular block diagram. Can you identify series, parallel, or feedback from this one?
No, sir.
No, sir.
No, as far as I can see, there is nothing in series, nothing in parallel, nothing in feedback directly. So normally when you do it by hand, you can perform some manipulations, but in using MATLAB, it's not possible to use series, parallel, or feedback. So we'll use topological reduction. So let's take a look at this example. So we have 6 blocks, 6 transfer functions, G1, G2, G3, H1, H2, H3. For simplicity's sake, we'll assume all the G's are similar and all the H blocks are similar. So let's define them using TF, very easy. So G1, G2, G3, H1, H2, H3. We have defined them. G1, 1 by S, G2, 1 by S, G3, 1 by S, H1, 1 by S plus 1, same for H2, same for H3. Okay, so the next step, you have to indicate to MATLAB that these 6 blocks are in a system together. For that, you have to use a command called append. Append, then write all the 6 blocks, G1, G2, G3, H1, H2, H3. The thing is, you have to use a particular order. So you have to give these blocks a particular order. So in this case, what we have given G1 as 1, G2 as 2, G3 as 3, H1 as 4, H2 as 5, H3 as 6. And you have to use this same order in this append command. So G1, G2, G3, H1, H2, H3. You cannot change this order. You cannot write H1 before G3. You cannot write H2 before G1. You have to follow this order. Now again, this is one order. You can use any order. So you can make G1 1, H1 2, H2 3, G3 4. The order doesn't matter which order you give, but you have to follow this order in this append command. Okay. Is it clear?
Yes, sir.
Okay, so use this append function for all 6 blocks. So now we have indicated that these 6 blocks are in a system together using the append command. But we have not yet indicated how they're connected. We have only indicated that these 6 blocks will be in a system. That's it. Next, we have to define the inputs and the outputs. What that means is you have to denote to which block is the input signal entering and out of which block is the output signal exiting. So in this block diagram, the input signal is RS, right? So which block is RS entering?
So block 1.
Block 1. And which block is the output exiting from?
Block 3.
Block 3. Again, remember this order. You have to follow this order all the time. So we just directly write input equal to 1, output equal to 3. That's it, directly. So input equal to 1, output equal to 3. The input is going into block 1. The output is coming out of block 3. Next is the main part. We have to write a connection matrix. Now this connection matrix will represent how all these 6 blocks are connected to each other, in what manner they're connected to each other. We have to do that using this connection matrix. So we have 6 blocks in this system. So for the 6 blocks, there will be 6 columns, 1, 2, 3, 4, 5, 6. And the first element of each column will be the block number, basically 1, 2, 3, 4, 5, 6. Now for each row, so basically the first row is for block 1, the second row is for block 2, and so on, right? So for each block, you have to denote what connections are going into that block, right? You don't have to care about what connections are coming out of that block, but you have to define which connections are going into that block. So in this case, into block 1. Into block 1. So the first row, you have to write which connections are entering block 1. So if you take a look at the block diagram, so if you take a look at block 1, how many signals are entering block 1?
2.
2. Yes, RS and V6S, right?
Yes, sir.
Where they're added together to make V1S. That's a good answer. But the thing is, we already defined the input signal previously, right?
Yes, sir.
So we don't have to count the input or the output. So for the connection matrix, you don't have to count the input or the output. So in that case, how many signals are entering block 1?
1.
Only 1, and it's coming from block 4, right? And it's getting subtracted, isn't it?
Yes, sir.
So beside the row for block 1, you just write block -4 to signify a negative signal that is coming from block 4. That's it. So we have done all the connections for block 1. And these zeros, they're placeholder zeros to make the matrix what? Rectangular, right? Okay, let's move on to block 2. So now we have to write which connections are coming to block 2. So take a look at block 2, this block. So how many signals are entering block 2?
1 and 5.
Yeah, as you can see, it's very easy to see V2S and V7S. So V2S is coming from block 1 and V7S is coming from block 5. But the block 5 signal is getting subtracted, right?
Yes, sir.
So for block 2, how will we write the connection? 1 and
-5.
yeah. So for block 2, it will be 1 minus 5.
Sir,
And
can
the
we
rest-
write? Sir, can we write -5 1?
Yes, you can write that. The order in which you write these connections, it doesn't matter. You can write 0 minus 5 1 0. Same thing. Okay. The order doesn't matter when writing the connection matrix. I mean,
Okay,
the
sir.
order of each block's connections. But obviously the order of the blocks matter. So it will be 1, 2, 3, 4, 5, 6 from top to bottom. But beside each block, the connection order does not matter. So let's move on to block 3. How many signals are entering block 3?
3.
3, right? V8, V4, and V3. So V8, it's coming from block 6 and it's getting subtracted. So that's -6. For V4, it's coming from block 2. So that's +2. What about V3? The top signal.
It's coming from G1 and H2.
Yeah, so
Block 1, 5.
yeah, so the signal V3, it's actually coming from two different signals, right? From block 1 and block 5. So for that, you have to write it as a summation of those two signals. So basically 1 and -5, right?
Yes, sir.
So for block 3, it's 1, -5, then 2, then -6. That's what we have written. 1, -5, 2, -6. The order doesn't matter. So
Sir,
did
sir,
everyone?
Sir, if we have more than 4 connections, then what will be the order of connection?
If you have more than what?
Sir, here we have, sir, 4 block connection.
Yes.
Yes, if we have more than 4 block connection, like 6 connection, then how can we write this matrix?
Write 6 connections. Add placeholder zeros so that it's rectangular.
So the order will be increased.
No, I said the order doesn't matter. You can write these connections in any order. So it can be 1, -5, 2, -6, or 1, -6, 2, -5. Same thing.
So, sir, the whole connection matrix order will be increased.
Do you mean if we increase the number of blocks?
Sir, মানে স্যার এখানে কানেকশন ম্যাট্রিক্সের অর্ডার তো স্যার দেখতেছি আমরা হচ্ছে স্যার 5 into 6 তখন স্যার অর্ডারটা কি বেড়ে যেত যদি আমাদের
Oh, achha, yes. Yeah, because you have to make the matrix rectangular. So if one of the rows becomes larger than the others, what do you have to do? You have to add placeholder zeros to the other rows, right?
Okay, sir.
Because if it's not a rectangular matrix, then it's not a matrix. So you have to make it rectangular. So for the other rows, these are just placeholder zeros. So as you can see, the third block has the highest number of connections, which are four connections, right? So you have to add zeros so that each of the other blocks also have what? Like 4 elements beside them. Is it clear?
Yes, sir.
Okay, so did everyone understand the connections for block 3?
Yes, sir.
This one was the least simple one. So the other ones are easy again. So for block 4, what will it be for block 4?
So it's coming from V4. So
It's coming from G2, block 2.
Yes, sir.
And any other connections? No.
No, sir.
So for 4, it will be just directly 2. That's it. For block 5, same thing, because as you can see, the same signal is entering block 5, right?
Yes, sir.
So for 5, it's coming from block 2, so it will be 5, 2, 0, 0, 0, 0. For block 6,
So block 3.
block 3 directly. So 6, 3, 0, 0, 0, 0. So that's how you write the connection matrix. This is the one that you have to think a little bit about. So otherwise, the whole thing is pretty easy. So just let's copy this connection matrix. So we have defined the connection matrix, the input and the output, and also we have defined that these 6 blocks will be in a system together. The only thing that is left to do is to connect all of them together. So For that, we use this function, which is called connect. Connect first our system, which we defined earlier using append, then the connection matrix, then the input block, then the output block. So just write this one. So this is the overall transfer function of the system, which we have obtained using the topological block diagram reduction technique. The thing is, this transfer function, can you tell that this is a transfer function?
No, sir.
Because this does not look like a transfer function. What does it look like? It's a state space model. It's another representation of a transfer function, but you don't need to know about this one. So how can we observe this in normal transfer function, in Laplace form, Laplace domain representation? Very easy. So we have final equal to, just use TF. Just use TF final. And this is the overall transfer function of the system.
Yes, sir.
Is it clear? So to observe it using the Laplace domain, just use what? TF. Now one extra line we have, which is called min real. Now min real is used to perform pole zero cancellations. So it is used to further simplify the transfer function. So what does pole zero cancellation mean? Suppose our transfer function is something like this. So G equal to S multiplied by S plus 2.01 divided by S plus 1.99. Suppose this is the transfer function. So what is the issue with this transfer function?
So the order of the numerator is higher than denominator.
I mean, yeah, but for, okay, I'm not talking about that issue.
Poles and zeros are very close to each other.
Yeah, so in this case, the pole and the zero, one pole and one zero, they're very close to each other. Basically, they're equal, right?
Yes, sir.
So is it correct to write it in this manner, or should we just write it as G equal to S?
We can simplify it to G.
Yeah, because the simpler our transfer function is, the simpler all our analysis will be. So our target is to always simplify the transfer function. So in this case, we'll perform pole zero cancellation when we write it by hand, but just by directly canceling them out, right?
Yes, sir.
But since MATLAB is a software, it will not do those distinctions. So in order to make MATLAB do that, we have to use the min real function. We have to do the min real function to make MATLAB perform the pole zero cancellations if they're possible to be performed, right? So
Yes.
again, if we take a look at our original transfer function, instead without using TF, don't use min real after using TF. Leave TF until the end, right? So originally we had final, right? So what if you make final equal to min real of final? So now we have min real dit. Then again use final 3 equal to TF final. So this is the transfer function that we get after using min real. Without using min real, what did we obtain? We obtained final 2. So can you spot the difference between these two?
Yes, sir. It is simpler.
It is much simpler. So after using min real, the transfer function that we obtain is much more simple compared to without using min real. And again, don't use min real after using TF. Leave TF for the end. Okay, and that is how we reduce a massive block diagram into just one single block with one single transfer function. So any question for this one? This is the most important part of this lab, I guess, this method. Any questions?
No, sir.
Okay, so let's take a look at a special case in the next page. This one. So this is another block diagram. It's not that complex. I mean, it's slightly less complex than the previous one. But suppose we want to reduce this block diagram using topological reduction, because as you can see, it's not possible to be reduced using series, parallel, and feedback. I mean, I guess you can do these two are in series and it's in parallel with this one. But after that, what? There's another signal that is coming out, so you cannot use series with this one. So for this one, you also have to use topological reduction. So can anyone tell me what is special about this case compared to the previous one?
No, sir.
Okay, one clue. Take a look at the input signal.
Sir, there are inputs going to block 1 and block 4.
So in this case, the input signal is entering two different blocks, 1 and 4. Previously, the input signal only entered one block, which was block 1, and we defined IP equal to 1 directly. But in this case, the input signal is entering two different blocks, block 1 and block 4. So in this case, we have to define two separate inputs, basically. Everything else will be the same, but for the input, how to denote the input, we have to write a matrix 1 and 4. This signifies that the input is entering both block 1 and also block 4. And the rest of the process, it will be the same as the previous one. But the end result, can you tell me what might happen at the end result? At the end?
No, sir.
So this system will be treated as a multiple input, single output system. So MATLAB will assume that there are two inputs to this system, and as a result, at the end, we'll get two transfer functions. Output divided by input 1 and output divided by input 2. Do you understand what I mean?
Yes, sir.
Yeah, so at the end, we'll get output divided by input to block 1. That's one transfer function. And we'll also get output divided by input to block 4, which is another transfer function. So we'll get two transfer functions. But the thing is, this is one single block diagram. And obviously, there's only one input, right? This is not a multiple input system. There's only one input. So the result that we'll get will not be incorrect, but it will be kind of incorrect, right? So how to rectify this?
No idea, sir.
The answer is very, very, very simple. So if you take a look at the next page, you can understand.
Yes, sir.
So what is the answer? Just by inserting an extra block at the input side, and that block will have a transfer function equal to 1.
Yes, sir.
So in that manner, we are not changing anything. Everything will be the same. But now we can say that the input signal is only entering one block, which is block 1.
Yes, sir.
And the rest of the things, it's the same manner as before. Append, then connection matrix. As you can see, the input is going into block 1 only, IP equal to 1. The output is coming out of block 4. So OP equal to 4. We have our system append, connection matrix, same. Everything is the same. So I'm not running this one. It's the same thing. You have very easy. So lastly, this is the transfer function that we'll get.
Yes, sir.
If you solve this system by hand, which is pretty easy to do, this is the transfer function that you'll get.
Yes, sir.
So if you take a look at the analytically calculated transfer function and the MATLAB simulated transfer function, so logically speaking, they should be the same, right?
Yes, sir.
But are they the same?
No, sir.
Can anyone tell me what is the key difference between them, the MATLAB one and the handwritten one?
Sir, it includes very small coefficients.
It includes very small coefficients like these ones.
Yes, sir.
And this one, right?
Yes, sir.
If you don't count them, they are the same. If you look carefully, without these very small coefficients, they are the same thing. just multiply the num and the den with 2.
Yes, sir. Yes, sir.
Does everyone understand this part? So
Yes,
in
sir.
MATLAB, it's a
Sir.
very precise software. So it will keep these very small coefficients. But the thing is, if you take a look at them, 10 to the power minus 16, 10 to the power minus 15, 10 to the power minus 16. What does that mean? They're 0.000000. I mean, they're basically zero, right?
Yes, sir.
So when you write them by hand, they will not even come. So you can basically say that they're negligible, they're zero, and you can directly omit them. And that's how you'll get the analytical result, this one.
Yes, sir.
Okay, so that's it. And so that is the end of this lab. You only have the lab task to do. This is also a part of the lab report, this one. So your lab task is to do this one. Do this one without adding any extra blocks. So that means basically keep the input as it's shown here. It's entering 2 different blocks, keep it like this, and then do the topological reduction method, obtain the overall transfer function or functions in this case, right? So that is your lab task. You can start immediately and you'll have up to 10, 10. Okay, I'll give up to 10, 15, but no more than that.
So can you
Any questions about the lab task?
can you repeat the question? What was the lab task?
So the lab task is the block diagram that we have, the special case. Reduce this block diagram topologically, but without adding that extra block. Without adding this extra block. So keep it as it is. Keep the figure like this. Make the input a vector 1, 4 because it's entering 2 blocks, and then reduce this block diagram using the topological method. Is it clear? Okay, so you have to write the code, obviously. Then attach the results in a Word file, upload that Word file in Google Classroom.
Sir, my electricity is not there. Can I picture?
If it's possible for you to do it by hand, is it possible? Write the code by hand. I mean, can you?
Sir, I can try, but I don't know if I can.
I mean, it's the same thing, right? It's a code basically. So you can write the code by hand and then like upload a screenshot.
Sir, can I just submit it later when my electricity is there?
Okay, you can do that, but if it's possible to do it by hand, you should do that. Write the code by hand, then just upload the photo. That's it. So I've created the assignments in Google Classroom. So just upload it there. You have up till 10, up to 10:15.